Hello, welcome to Engineers Mindsets. So, in today's class, we are going to be talking about the second law of thermodynamics. Now, before talking about this law, let's just do a brief revision on the first law of thermodynamics. Remember, the first law of thermodynamics states that for a closed system undergoing a cyclic process, the net heat transferred from the surrounding to the system equals the net work done on the surrounding by the system. So the first law is actually what? A law of conservation of energy. But that law did not actually give us the direction of heat transfer or the direction of work that is done. That first law didn't actually give us these directions. Now, if I consider, let's say we consider a cup that contains a hot water, and of course we place this cup outside atmosphere or under atmospheric conditions. What happens is that after some time, this hot water becomes cold, but not necessarily because cold was transferred from the surrounding to the cup of hot water. No, but simply because the heat was actually what lost from the cup containing the hot water. So that actually means that there is actually what a direction of heat transfer from the cup of water to the atmosphere or to the environment. So therefore, the hot water loses heat and then becomes cold. Another example also, let's say you bought a certain amount of fuel or petrol in your vehicle or in your car, and then you drive some distances forward, and then you also follow that same path which you follow forward. You follow the same path backwards. Notice now that the amount of fuel or petrol you burnt moving forward cannot be restored or recovered. So this analysis, these observations led to the formulation of the second law of thermodynamics, because the first law did not actually give us the direction of heat transfer or direction of work transfer to the system. But the second law actually gives us what an accurate idea of how this heat is being transferred or how this work is being done. So without wasting much time, let us dive into the second law of thermodynamics. The second law of thermodynamics simply states that it is impossible to construct a system which will operate on a cycle, extract heat from a reservoir, and do an equivalent amount of work on the surrounding. So the law is basically saying that it is very much impossible to convert the entire heat coming into the system into work, unlike what the first law says. The first law says that heat transfer from the surrounding to the system is equal to the work done on the surrounding by the system. And mathematically, that law simply gave us that heat transferred is actually what equal to work. But the second law is simply saying that it is very much impossible for us to what convert the entire heat coming into the system into work. It's very much impossible. So it means now that a certain amount of heat must be lost before work is being done on the surrounding. That's what the second law is saying. That it is impossible to construct a system which will operate on a cycle, extract heat from a higher reservoir, and do an equivalent amount of work on the surrounding. It's very much impossible. So which means a certain amount of heat must be lost before work is being done on the surrounding. Now, a key word that has been mentioned here is actually what? A reservoir. What is a reservoir? A reservoir is simply a special kind of a system which do not increase in temperature or reduce in temperature regardless of the amount of temperature added to it or removed from it. It can also be defined as a special type of system whose temperature is kept constant regardless of the amount of temperature taken from it or the amount of temperature removed from it. So its temperature is actually kept constant. An example of a reservoir is simply the Earth atmosphere is a reservoir. Regardless of the amount of heat you burn into the atmosphere, you cannot feel it on every part of the atmosphere. So it can neither increase nor decrease. Also, a large water body like the ocean or the sea are also good examples of a reservoir. No matter the amount of heat added to or removed from the ocean, it doesn't change the temperature, it remains the same. All right, so we have said that the second law actually operates between two reservoirs. So one must have or supply temperature at a very high intensity, and the other must be where the heat is being or the temperature is actually being rejected. That's the temperature or the low, that's the low temperature reservoir. So the second law of thermodynamics actually operates between two reservoirs. First reservoir is at a higher temperature and the next reservoir is at a lower temperature. Let's draw a sketch now and see. Okay, so this is a perfect example of what the law is saying. The law simply says that, of course, before work is being done on the surrounding or before work is being given out, some intensity, let's say we have a heat here, Q1 coming into this system. Let's call this Q1, the heat intensity coming into the system. The law is simply saying that this system cannot convert this entire heat into what work on the surrounding, but rather the system will reject some certain amount of heat to where a low temperature reservoir. So this is a high temperature reservoir which is supplying the heat. So it can be called the source. Okay, this can be called the source, a high temperature reservoir. This is where the heat is actually coming from. Now the heat gets into the system. The second law simply says that this system must first of all reject a certain amount of heat. So let's call this what Q2, which is the amount of heat this system rejects into where a low temperature reservoir. Now when this is achieved, the system cannot do work on the surrounding, and then the work done is actually difference in what the heat supplied. We can simply call this Q1 minus Q2. So which means the intense heat, the first heat coming into the system minus the second heat coming into the system, that gives us the work done, okay, on the surrounding. So the intensity of heat coming into the system cannot completely be converted into work, just like the first law says, but rather this heat must first of all be rejected into a low temperature reservoir before work is being done on the surrounding. And that work done is simply what? The difference in heat supplied and then the heat rejected. Now, the temperature, the high temperature reservoir actually has an initial temperature which is T1, which is where which is likely to be the source, that's where the temperature or the heat is being supplied from. Meanwhile, T2 is actually what? A low temperature. So the work done itself can also be given as T1 minus T2, which is simply the difference in the high temperature and the low temperature. This can also give us the work done. Now, such a system which operates in this manner, that is supplying temperature from a high reservoir and then rejecting to a low reservoir before doing work on the surrounding, is what is called the heat engine. We simply call this system a heat engine. Okay, so a heat engine actually operates in this manner, supplies temperature from a source or from a high reservoir, rejects some of the temperature or the heat into where a low reservoir before doing work on the surrounding. So such a system is actually called a heat engine. Okay, now the second law of thermodynamics, which I've stated here, is according to Kelvin-Planck's statement of the law. Now we have we have a corollary aspect of the law, which was made by Clausius, but then the law which I've said so far is according to Kelvin-Planck's statement of the law. Okay, and of course, the Kelvin-Planck statement of the law is being governed by the principle of the heat engine. Now, what then is the Clausius statement of the law? Okay, what then is the Clausius statement? What then is the Clausius statement of the law? Now, the Clausius statement of the law simply states that it is impossible to construct a system which will operate on a cycle, extract heat from a cold reservoir, and supply towards a high temperature reservoir without work being done on the system. Okay, so it is simply saying that if cold is actually being transferred to heat, or heat is being supplied from a cold reservoir down to a hotter reservoir, then invariably we are actually what doing work on the system. So that is actually what a reversed heat engine. It is actually a reverse heat engine. And the principle of reverse heat engine is actually the principle of the refrigeration system or the heat pump. So it is very much impossible to construct a system that will operate on a cycle and then heat is being extracted from cold reservoir to a hotter reservoir without work being done on the system. And remember, whenever a system loses heat, then work is being done on that system. The heat loss is actually negative and the work done on the system is also negative because work is now being done on the system. All right, so if we draw that diagram, we're simply going to have, okay. All right, so according to Clausius statement, like I said, it is actually what a reversed heat engine. So now heat is being supplied from a low temperature reservoir. So you simply have here, okay, simply call this Q1. Heat is now being transferred from the low temperature reservoir down to where the high temperature reservoir. Simply call this Q2. And of course, since this is low, this is T1 in this case because this is now the source and this is now the sink. So the cold is actually coming from the low temperature reservoir down to a high temperature reservoir. So simply call this temperature T2. Okay, so the law is simply saying that if this is achieved, then work is actually being done on the system. If this is achieved, then work is actually being done on the system. And that work, of course, still remains Q1 minus Q2. This work still remains Q1 minus Q2. But this work now is going to give us what? A negative value, where Q1 is what? Initial heat, okay, which is the heat supply from the source. And then Q2 is where heat rejected or rejected into the high temperature reservoir. Okay, so still the same thing. Work done can also be changed in temperature, which is T2 minus T1. This also gives us the work done, but in this case, this work is definitely going to be negative. So as can be seen here now, this is actually a reversed heat engine. Instead of it to come down from the high temperature reservoir to the low temperature reservoir, we now experiences that heat is actually moving from the low temperature reservoir down to the high temperature reservoir. So it is actually called a reversed heat engine. And the system that operates in this manner is actually called the heat pump or the refrigeration system. Okay, you can call that the heat pump or refrigeration system. Okay, so the system that operates in this manner is actually the heat pump or the refrigeration system. All right, so having known this now about the second law of thermodynamics, let's now talk about the efficiencies of the heat engine and of course, if possible, the heat pump and the refrigeration system. Okay. All right, so we all know that efficiency is actually the work done on a system or simply the work output all over the heat supplied into the system. So we can have here efficiency, okay, is simply work done all over heat supplied. So if we examine the heat engine, we are going to observe that, and that work done has two formulas. First, we said the initial heat minus the final heat, and then initial temperature minus final temperature. That gives us the work done. So we can simply have that efficiency. Please, you always multiply by 100%. Okay, so efficiency is now equal to work done was given as Q1 minus Q2 all over Then we said heat supplied, and of course the heat is this coming from the heat is actually supplied from the high temperature reservoir, and that simply was Q1. So we can simply have this will be Q1 minus Q2 all over Q1 multiplied by 100%. So this is actually the efficiency for a heat engine. We can also write this for in terms of temperature, still the same thing. Work done is simply T1 minus T2 all over the initial temperature or the inlet temperature T1, okay, multiplied by 100%. So that's how you calculate or find the efficiency of a heat engine using what? That simple formula. Meanwhile, for a heat pump, it's basically the same thing for a heat pump or the refrigeration system. But in this case now, the refrigeration system or the heat pump operates on what? Reversed heat engine. Okay. So the refrigeration system and the heat pump actually operates on a reversed heat engine mechanism. Okay, so we can simply say for a pump, um, for the pump, okay, the efficiency instead of saying work done over heat supplied, it becomes the heat supplied. So it is reversed heat supplied, okay, all over the work done, okay. So which means efficiency, which means efficiency is actually heat supplied now is simply Q1. So you simply have Q1 all over the work done, which is still Q1 minus Q2, okay, multiplied by 100%. All right, so just to point out, the heat pump actually do not have an efficiency because if you carry out this analysis, you're actually going to have that these values will be greater than 100%. It will definitely be greater than 100%, and there's no machine in life that is actually 100%. Even the ideal machines are not real. They are not real. They are simply ideal, so they are not real in life. And of course, there's no machine in life which is 100% efficient. All right, so the heat pump is not actually called efficiency for the heat pump. Instead, it is simply called coefficient of performance for the heat pump or for the refrigeration system, because if you carry out this analysis, you have more than 100%. So it is called coefficient of performance. So instead, please simply change it to what? Coefficient of performance. So we'll simply use COP. Okay, so coefficient of performance for a heat pump is simply given as this: the heat supplied all over the work done multiplied by 100%. Same thing applies here. Instead of efficiency, it is simply called coefficient, okay, for a heat pump. All right, so this is called the formula for the coefficient of performance for a heat pump. All right, so basically the principle of refrigeration system also works in this manner. Of course, also works in this manner. All right, so I'm going to pause the video here, and in the next video we can start calculations on applying how to apply these formulas to find the efficiency of a heat engine and also the coefficient of performance of heat pumps and probably refrigeration system. All right guys, thanks and cheers.